So in the discussion that we had yesterday, we started talking about the different kind of mean difference tests, right? So what we did over there was we had discussed about the mean difference tests like the single t-test, the mean difference t-test. Within there, we had discussed about independent sample tests, and we had talked about the paired sample t-test. And from there, we had talked about the role of the t-tests, the mean difference tests, especially in the domain of risk analytics. Right? So, where is it that we would like to use this mean difference tests? So, post that, what we had done was the following: we had created a kind of what should I say? So we had created kind of examples and we explored the cases where this mean difference test comes into play. After that, what we started off doing was we started off talking about the ANOVA. So if the groups have more than, so if there are more than two groups of values, then if there are more than two groups or more than two or more groups, then what we use is ANOVA. ANOVA is defined as the analysis of variance. So when we talk about ANOVA or the analysis of variance, right? So over there, our objective is as follows. So what we are trying to do over there is we are trying to assess the significant difference in the mean by exploring the variances. So what I'm trying to do is I'm trying to understand, okay, this is what the overall variance is across the groups. This is what the variance is within the groups. And from there, what I'm trying to do is I'm trying to frame up a particular kind of analysis, right? So what that is what I'm trying to do. So I'm trying to assess the significant difference in the mean of the groups by comparing the variation across the groups, right? So this is what is the idea behind ANOVA. So what are we trying to actually do over here? So let us say, for example, we are building a puzzle model for a credit card. So over there, what we get to see is that there are three segments which can be created. One is a delinquent segment, the other is a non-delinquent segment, and the third is the inactive segment. Now we know that for the inactive segment, we need not develop any kind of other kind of models and such. So what we generally do is we identify we just look into the, so we just need to keep that as a separate segment and estimate a separate a probability for that, right? Because inactive segments do not have sufficient performance information for us. So on the other hand, the model would be developed for delinquent and non-delinquent. But to know whether these three segments, the segment that we have created over here, so whether this segment is a proper segment or not, right? So what we need to do over here is we need to actually assess as to how the behavior is like. Okay. So how is it that so whether these two segments are stable or not, and to assess the stability of the segment, we need to understand what is the mean difference test and what is. So we need to understand that the bad rates across the segments are significantly different, and that they are significantly different over all points of time. So it must satisfy the significant difference in the mean across the segments, as well as it must satisfy the rank ordering issues. So that is what we have been trying to do, and this is to assess the stability of segments, to assess segmentation, is one very important area where this particular method comes into play. Right. So this is where, or rather, so this is what we have been trying to do over here. Now comes the next part. So that is so the next question that we want to understand over here is that how is it that we are deploying ANOVA? So we saw that to deploy ANOVA, to get an idea about the descriptive measures from ANOVA, we need the following two information. One, we need across the group variation, get the across the group variation. Across the group variation. And over here, what we could see is the variation within the group is known as within the group variation, or we call it the intra-group variation. So this is idea within the group variation. This the within group variation. Right. So this across the group variation is also known as the intergroup variation. This is known as the intergroup variation. Is known as the intergroup variation. And over here, the next part that I have is the intra-group variation. The intra-group variation. So on one side, what I have is the across the group variation, and the other is the within the group variation or the intra-group variation. So these are the two things that we have. So over here, if you look into this intergroup variation that we have. So what is the intergroup variation? The intergroup variation is the variation which we can actually explain. So that is, it moves as I move from group A to group B, or from group B to group C, I can say that yes, there is a variation, and yes, I can actually explain that variation. So this is what the intergroup variation is. Now, after this intergroup variation, so from this intergroup variation is also known as the explained variation. This is known as the explained variation. Variation. Now, why is this called the explained variation? This is called the explained variation because you can explain why this variation is occurring. The fact that this variation is occurring as you move from x1 to x2 and x2 to x3. So this is called the explained variation because actually you can explain this variation occurring. And the second that we have over here is the next that we have over here is the intergroup or the intergroup variation, which is the within the group variation. So what is this intra-group variation that I have? The intra-group variation that I have over here is the following. So over here when I talk about the intra-group variation, what we are trying to talk about is the variation within a particular group. Now within a group, why a variation is occurring, that may not be possibly said because all the observations in a group is homogeneous in nature. So over here, this intragroup variation that I have is an unexplained variation. Is known as the unexplained variation. Variation. Right. So there is intergroup variation which is explained variation, and there is intergroup variation which is the unexplained variations. Right. So this is what. So over here, what we are actually trying to do is we are trying to actually compare these two variations. So now if I see that so as I move from one group to another, the overall variation is very distinct, it's very high or it's very prominent, then I know that it is an explained variation. So I move from group A to group B and group B to group C. I see that there is a very prominent movement or there is a very prominent change in the variation. But as I move from, I mean, within a group, I see that the overall variation within a group is not very high. So what does it mean? What it means is that observations within that group is more or less homogeneous in nature. Whereas the observations that I have across the group, so as I move from group A to group B and group B to C, that across the group that I have, the observations that I have, that is precisely very different. Therefore, this is where we have the across the group variation, and this is where we have the within the group variation. So these are the two parts that we generally have, right? So is this part clear? Great. So over here, so there would be a within the group variation, and then what we would also see over here is there's the across the group variation and so on. Now what we would like to do over here is the following. That so when I talk about the across the group variation and within the group variation, so what I have is explained variation, unexplained variation, and so on. So the next question that we need to ask ourselves is, how do we identify or quantify this explained variation? How do we quantify this unexplained variation? Right? So that is where the next part that we take up. So over here, uh, how do we, the first question before we go into even to talk about explained and unexplained variation, let's understand how do we explain variation. So in statistics, mostly what we do is we explain variations through we explain variations as variations. So variation is defined as a dispersion about the mean. So variation in statistics is defined as uh, Suri, just give me a second and I'll continue. So as I was saying, so when I talk about variations, right? So variations will so as I said that variations are computed about the average, right? So this is dispersion about the mean. So dispersion about the mean. So when I talk about so over here when we are talking about variation, we are talking about dispersion about the mean. So the question that next comes out is that how do we define the dispersion about the mean? So when I talk about dispersion, so how do we take the dispersion about the mean? Now dispersion is nothing but sum square of the deviations. So that is summation I equals to 1 to n. So this is your expression for dispersion. So xi minus x bar whole square, right? So this is summation I want to n xi minus x bar whole square. So this is the expression of the total variation that you have about xi's, right? So just to very quickly recapitulate the stuff that we have done till now, we'll just quickly recapitulate in a minute. and then we'll move forward, right? So we are talking about ANOVA, which is nothing but the analysis of variance, and our objective is to compare the variation across the groups and within the groups for the two or more groups for which we are computing mean difference. So in ANOVA, we are exploring the variation across and within the groups to identify whether there is a significant difference in the mean or not. So over here, what we have is the variation, which is the dispersion. So basically what we saw was that the across the group variation is, or known as the intergroup variation, is nothing but the explained variation, because that is the source of variation which I can explain. So I can say that, hey man, look, as I move from A to B and B to C, you will see that, or you'll observe that the mean is changing or the behavior is changing, and I can actually explain that source of the variation. On the other hand, when I talk about the within the group variation, right, so there is the intra-group variation that I am talking about. So when I talk about this intra-group variation, the intra-group variation is the variation within a given group. Now, given that the observations within a group is more or less homogeneous, we should not, or observations have similar characteristics. Ideally, they should not have any dispersion. Now, if they have a dispersion, that is really not explained. So that is due to some unexplained or some random factors, right? So that is what is the concept of the intra-group variation. So the intra-group variation is known as the unexplained variation, because the variations within a group cannot be explained. And when I put these two together, right, what I'll get is my ANOVA measure, my measure for testing the significant difference in the mean of the two groups, right? So what I need to understand over here is that how is it that this is going to come out. So over here you will see one thing, right? There is one important thing that you can see from here. So over here what we see is that we want to compare the variations across the two groups, right? Across the groups and within the groups to get a mean difference. So once I see that the variation across the group is a very prominent source of variation, and the variation within the group is not that significant, then I would know that the ratio is very significant, right? So then I can say that yes, there is a significant dispersion about the mean. Correct? So therefore, the next stage that we started taking up was we started talking about the concept of dispersion. How is dispersion measured in uh, statistics? So we measure dispersion in this particular way. So we measure dispersion from the observation mean, from the mean of the set, right? It's measured as a sum squared deviation, or sum of squared deviations. Sum of the squared deviations. So over here what we have is summation I1 to n xi minus x bar whole square. So sum of the squared deviation. So over here, so basically, what we need to do is we need to compute. So always there would be two types of means, right? One is an across the group mean, and the other is your within the group mean, right? And we compare the variations about them. Now, since it is, since we can see that this estimation is done about the mean, right? So therefore, what we get to see is it is summation xi minus x bar whole square, right? So it is summation xi minus x bar whole square. Therefore, so this is known as the sum squared deviation, right? Or as we call it, we can call it the explained sum of squares. This explained variation can be called the explained sum of squares. Can be called the explained sum of squares. This is known as the explained sum of squares. Explained sum of squares. Now the next part that I have is over here is the unexplained sum of squares. Right? So what is the unexplained sum of squares? The unexplained sum of squares is the intra-group variation, right? Or this is known as, or this is also known as the residual sum of squares. This part is known as, or this sum squares of errors are known as the residual sum of squares. Sum of squares, or as we call it, the RSS. Sum of squares, which is known as the RSS. Right. So there is a residual sum of squares. Now our objective over here is to compare between these two, the explained sum of squares and the residual sum of squares, and thereby try to identify whether there is significant or whether the mean difference is significant or not. So how can we do this? What would be the intuitive logic? So let's forget any statistics or anything. Let's just try to think about the experiment. So one part is I'm looking into the explained variations. As I move from A to B and B to C, what I'll get to see is that there is a movement across the groups, right? Now the question that comes out over here is that uh, the question that comes out over here is that how do I know that the explained sum of squares is more than the residual sum of squares? So what I say is the following, that corresponding to, say, a given explained sum of squares, so corresponding to a given ESS, Or let's put it like this, corresponding to a given RSS, a given RSS. So corresponding to a given RSS, uh, we have some value of ESS, right? Or corresponding to given RSS, the explained variation is what? ESS. The explained variation is ESS. Is ESS. Right. Now, similarly, corresponding to a unit value of RSS, of RSS, the explained variation is what? ESS by RSS. Is ESS by RSS. So over here what I can see is that the ESS by RSS will be some value, right? ESS by RSS will be equal to some multiple, right? So ESS by RSS will be equal to some multiple. So what is this multiple that I have over here? So it says that the ESS is some x times the RSS. So ESS is some x times RSS. So the problem that we have with us in our hand is that does this x, is this x a significant multiple? So is this x a significant multiple? Is this x a significant? Is this ESS a significant multiple? Clear? So, and to test, and our objective over here will be to test whether this is a significant multiple or not. Right? So, is the intuition of this test clear? So, what I want to know is that as I move across the groups, I get to see a variation. When I move within the groups, I get to see a variation. So, is this ESS by RSS? Is this a significant? So, is the ESS or the across the variations or the explained variations are the explained variations a significant multiple of the residual variations. So this is what is ESS by RSS. And that is why we are trying to test for the significance of this value. Clear?
Yes, Tanu.
Okay, great. So now the question that comes out over here is there are three questions. How do we compute ESS? How do we compute RSS? And how do we compute or how do we test whether it is a significant multiple or not? So over here you can see that we are comparing to variations. Therefore, this is a case where we are using a set of variance tests to assess a mean difference test. So over here what we are trying to do is we are trying to assess the variances. We are trying to compare the variances. Right. So we are trying to compare the variances over here or a variance test to frame an idea about a mean difference test. And the variance test that we use, since we are comparing the variances, the variance test that we are using is known as the F test. So we use a F test to get the variance test. Now, the details of the F test is provided in the documents that I have shared out with you. So over here, now the next question is how do we compute the ESS? So how? So let's take this particular example. So over here I am computing the expected or the explained sum of squares. So how does the mean for the explained sum of squares look like? So over here, one case, what I'll do is I'll take the average of these three. So if there are n observations, if there are n rows of observations, that means for each of the rows of observations there will be a mean which will be computed, right? So over here, what would change is so the mean for the first row will be say x bar 1 1. For the next one, it will be x bar 2 1 or say 1 1 2 1 3 1, right? X bar, okay. So it will be x bar dot 2. So what we'll say is that for explain sum of squares, if there are n number of observations, if there are n rows, if rows in the data equals to n, then the mean is also equal to n. So if rows equals to n, then the mean is also equal to n, right? So this is what the overall idea is. So ESS, if a row is equal to n, then the mean is equal to n. Now over here, so that means, so how do we compute the expected sum of squares? So first of all, let's look into for row equals to 1. So for the first row, how does it work? Your mean over here will be, I'd say, let's call this mean x bar dot 1. So this is x11. This is x21, x31. X bar dot 1. This is how I have computed the, for the first row, this is what the mean looks like. Now I need to compute the explained sum of squares for this particular row. For this particular row, I need to compute the explained sum of squares. So this is over here x11 minus x bar dot 1 whole square plus x21 minus x bar dot 1 whole square. X31 minus x bar dot 1 whole square. So this is what is the explained sum of squares for row 1, right? So like this, it will be, this is ESS for row 1. Like this, we compute the ESS for all the rows. Then the total explained sum of squares will be, so over here you will see that this is the ESS for the first row, right? ESS 1. After this is ESS 2. So after this is ESS 3. Right? So this is what ESS is. This is ESS 1, ESS 2, ESS. Right. So over here ESS1, ESS2, ESS, and so when I add all of these up, what I'll get is the explained sum of squares. So similarly, the residual sum of squares will also be computed, right? So this will be, so the number residual sum of squares, or the number of mean for a residual sum of squares, will be equal to the number of columns. So for RSS, if columns equal to n, equal to n, right? Then the mean will also be equal to n. The number of mean will be equal to the number of columns. So if column equals to n, then the mean is equal to n. This is what is RSS, right? Suchi, is this clear up to this point? Just check through it. Then we'll start the next one. So are we okay with this concept? Great. So when I have a multiplication of this, so when I do this, the next thing that I get to see. Okay. So over here, let's think about it in this way. So the next part is, so over here how do we compute the statistics? So over here it is, so the statistic that we compute over here will be a ratio of two variances. It is explained sum of squares by the residual sum of squares. So over here you see that there are two different, so there is a ratio of two variances, right? So this is the F statistic. Now to define this, I require another important concept, which is called the degree of freedom. So the next question that, or the next concept that we need to start off with is called the degree of freedom. Now each of these, if the ESS has its own degree of freedom, so ESS divided by its degree of freedom. The RSS divided by its degree of freedom will result in wave statistics. This is the degree of freedom. Right? Okay. So over here, before we go in, so we'll not go into the degree of freedom concept right today, right? So let us we'll start off with this concept and the testing of this concept tomorrow onwards, right? We'll finish this part and then we'll take up the next. So today is sorry, tomorrow there would be no session, Suchi. The next two sessions conducted would be on Saturdays and Sundays, 7 a.m. to 8:30 a.m. Right? So we'll complete this
Okay.
part and the remaining whatever is remaining on statistical testing by Sunday.
Hmm. Okay.
Okay. And by today, tomorrow,
Okay.
I'll share over all the other recordings that are there with me, along with these board works.
Okay. Okay.
Okay.
Thank you.
Thank you. Bye bye.
Bye bye.
Bye.